Hey there folks, I'm picking back up where the last video left off. After building and installing the front panel harness, we'll transition to a simpler task, installing the primary NVMe drive. On the front of the motherboard, I'll remove the Gigabyte branded protective film from this NVMe pad. Next, I'll gently insert the drive into the M2Q_SB slot, and then push it back and up until the edge catches on the easy latch clip. With the GPU in place, 2 of the 4 screws on the motherboard heatsink will not be able to be used, so I removed them with a Phillips screwdriver. Additionally, to make the heatsink a little easier to slide into place, I removed the thermal pad that corresponds to the M2C_CPU slot on the motherboard. This size of thermal pad is easy to find on Amazon, so if I need to add it back to support a different configuration in the future, I'll be able to find one with ease. Lastly, I'll remove the protective film on the heatsink thermal pad for the NVMe slot I am going to be using. Carefully, I'll slide the right edge of the heatsink under the edge of the GPU, and once it's in place, use a mini Phillips screwdriver to reattach it to the motherboard. This heatsink serves 3 purposes. It transfers heat away from the NVMe, it transfers a small amount of heat away from the chipset heatsink, and it covers the Gigabyte branded protective film on each of the remaining NVMe slots. One thing to keep in mind is that by using only 2 of the 4 heatsink mounting screws, there isn't as much downward clamping force as there would be if all 4 screws were used. I've not personally ran into any problems with using only 2 of the screws so far, and I've done a lot of in-depth thermal testing, but just be aware of this fact if it were to be detrimental in your own setup. With the heatsink reinstalled, we can move on to installing the SAS HBA. I'll insert the card into the bottommost or leftmost PCIe slot on the motherboard and secure it using a standard bezel plate screw. The specific card I'll be using is the LSI 9305-16i, which provides direct connection for 16 SATA drives and many more if using SAS expanders, which I won't be using in this build. This model is an internal card, indicated by the 16i, where the I stands for internal, and there are no ports or connectors on the bezel plate. Most HBAs and RAID controllers get really hot, and this heat needs to be managed to prevent the card from dying a heat death. I think every storage card I've ever used has had a line in the user manual stating that some form of direct cooling is necessary, and my experience has aligned with that statement. I've designed this very simple mounting arm that will attach to the frame via 2 M5 screw holes at the top, and on the bottom, there is a curved section that perfectly mates together with a 60mm computer fan. Using 2 standard fan mounting screws, I'll attach a Noctua NF-A6X25FLX to the mounting arm. I've oriented the fan so that the airflow created by the fan will be blowing directly on the heatsink of the HBA. Between the 2 support brackets for the water pipe, I'll roll in 2 T-nuts and attach the arm using M5 15mm screws. Positionally, I want the fan blowing directly on the largest area of the HBA heatsink fins, so if it needs repositioning to achieve that, I'll do so before tightening it down completely. To connect this fan to the motherboard, I'm going to move a couple things around. You'll recall earlier when I built the pass-through box that I said I don't use the tack feature of the pump, but I went ahead and built the cable and attached it anyway. For now, I'm going to make the following changes to the fan header arrangement near the pass-through box. Unplug the tack cable from the motherboard and tuck it out of the way. Move the 4-pin cable that supplies power to the left side radiator fans from the sys_fan4 header to the sys_fan5_pump header. Plug the 3-pin connector for the HBA fan into the sys_fan4 header. And finally, tuck things away and add a small zip tie to the wires to keep things tidy. Let's move on and get the SATA cables connected. SAS to SATA breakout cables have one Mini-SAS SFF-8643 host connector on one end, and 4 standard SATA connectors on the other end. These cables are very stiff. They cannot be bent left or right at all. They can, however, be twisted to some degree, as long as you have a decent sized space to initiate the twist. The shrink tubing and sleeving make it even harder to get these cables into tightly cramped spaces. I'll walk you through what I do in my builds to squeeze some additional bendability from these cables, but bear in mind, once I remove the sleeving, I'll need to be even more careful to prevent damage to the wires, since there won't be any shielding to protect them. I'll slide the tip of the flush cutters under the edge of the heat shrink and very carefully snip along the full length of the heat shrink. Once the heat shrink is split, I'll use a pair of scissors to cut the sleeving all the way back to the protective tape below the 8643 connector. If necessary, I'll use the tiny edge of the flush cutters to trim back any remaining sleeving strands. This leaves us with only exposed data wires along the full length of cable. I'll repeat this for all 4 cables I'll be using. 3 of those cables are 1.6 feet in length, and 1 of the cables is 3.3 feet in length. To route these cables from the HBA to the drives on the rear of the frame, I designed this simple mounting block. It has 4 tracks, 1 for each of the 4 cables, has filleted edges where the wires are inserted to prevent nicking the cable sheathing, and has a total bend radius of roughly 30 millimeters. The depth of each track allows the 8 wire groups on each cable to stack perfectly on top of one another in the track, and a cover is used to make sure they don't slip out. Behind the door hinges, I'll roll 1 T-nut into the horizontal channel just behind the top hinge, and 1 into the backmost vertical channel. Next, I'll hold the mounting block in place and thread an M5 10mm screw into the vertical T-nut, and then thread another in the horizontal T-nut. Once both screws are started and the block pushed as high up as it will go, I'll tighten each screw down completely. To prepare each cable, I'll loosely attach 3 to 4 4-inch zip ties about an inch apart on the side of the cable with the 8643 connector. This helps to keep things in line throughout installation. However, they are not cinched down as far as they will go, as that would damage the individual wire groups. I like to work my way from the back of the SAS card to the front, so I'll insert the connector for a 1.6 foot cable into the back slot, which is labeled for ports 12 through 15. I'll push the SATA connectors through the slot behind the door, and then carefully feed the wires into the back channel of the SAS cable block. On the back of the frame, I'll temporarily add a piece of tape to the SATA plugs, just so there is enough tension that the wires don't fall out of the SAS block while I'm working. I'll repeat these same steps to plug all 4 cables into the SAS card. The order of the cables from back to front is the 3 1.6 foot cables in the 3 back ports, and the 3.3 foot cable in the front port. To ensure the wires stay put in the block and don't work their way free, I'll use this simple cover. It is attached to the block using 3 M2.5 6mm screws. With the cover added, we've finished attaching and routing all 4 SAS cables to the system. Let's move on and talk about how I'll be adding the actual SSDs to the system. I've designed this simple rack to hold the 20 SSDs that will be added over time. Although the rack itself could hold 21 drives, one of the slots will be used as a pass-through hole for me to route the 4 motherboard SATA cables through, bringing the total number of drives down to 20. 16 of the 20 drives will be connected via the SAS card, and 4 of the drives will be connected to the motherboard. Each column can hold 7 drives as designed, with roughly a 4mm air channel gap above and below each drive. It's assembled using M2.5 12mm screws around the perimeter of the front bezel, M2 8mm screws in the interior wall screw positions, M2 12mm screws on the top and bottom plates, and M2.5 12mm screws on each side plate. The SSDs slide in from the back and make contact with the front bezel, which prevents them from sliding out. There are M2 threaded holes on the top and bottom edges on the back to mount whatever attachments I might need to keep the drives in place and the wires organized. To mount the rack, I'll start by popping the clevis pin out of the door clasp and opening the door, which whoa dizzle leads to a door. In the bottom bar, I'll roll in 2 T-nuts, sit the rack in place, slide it so that the rightmost mounting screw track lines up with the rightmost T-nut, and then lightly thread an M5 10mm screw. Next, I'll slide the rack to the right so the middle mounting track lines up to the second T-nut, insert another M5 10mm screw, and lightly thread it into place. Finally, I'll slide the rack fully to the right, insert a third T-nut into the slot, push it with a hex wrench to align with the remaining mounting screw track, and lightly thread another M5 10mm screw. Before I make final adjustments, I'll push the rack as far against the right side aluminum that I can, and tighten the screws so they are more secure, but still allow for a little play in the rack's positioning. Throughout the mounting process, I'll be opening and closing the door to make sure there is ample clearance between the 2 components. Speaking of clearance, there is one area that needs some focus before I can fully lock in the position of the SSD rack, and that is the 4 downward-facing SATA plugs on the motherboard. As you can see here, with traditionally inflexible downward-facing SATA cables, the SSD rack can't slide as far forward as I'd like it to. At best, this would result in less air flowing over the SSDs since they'd be sitting further away from the fans, and at worst, I could break off the motherboard SATA connectors with enough force. I don't like either of those outcomes. To make sure the motherboard SATA cables aren't impediments to my success, I'll be using these SATA angle adapters to change the direction the cables are plugged into the ports, and we'll also be using these low-profile SATA cables that have significantly less insulation around the wires, making them easier to place and bend. Before putting the SATA angles in place, I'll add an M5 6mm screw to the front edge of the motherboard tray metal that apparently has went unaddressed until now. Next, I'll insert the two SATA angles into the two motherboard SATA ports. I've inserted the actual SATA cables into the angles prior to decrease the amount of total overall force applied to the motherboard connectors. With the angles in place, I'll gently slide the SSD rack forward to the point where it looks like it will be very close to making contact with the door once it closes. What I don't want is the rack and the door to make contact with one another, though I do want them to be pretty close, with only a few millimeters of space separating them. I'll also continuously check throughout the mounting of the rack that the door shuts properly and doesn't egregiously bend the SATA cables when it makes contact with them. From the back of the frame, I'll verify the lock nuts on the door and the front of the rack are close but not touching. It's also important to verify that the right edge of the rack is pushed solidly up against the right side of the frame metal. Once I can confidently sing, I'll use a hex wrench to fully tighten down the 3 screws securing the bottom of the SSD rack to the bottom of the frame. After I've tightened the 3 screws down completely, I'll use a millimeter ruler to measure the distance from the back of the frame metal to the back edge of the rack. On the left side, it's sitting perfectly at 40 millimeters, and on the right side, it's also at 40 millimeters. Next, I'll add the small clasp that keeps the 4 motherboard SATA cables in place on the rack. This is a simple clasp that has 2 mounting through holes and a rounded front edge that the wires can safely be draped over without damaging the wires. I'll bunch all 4 motherboard SATA cables together, lift them up, place the clasp around them, and then attach it to the SSD rack using M2 12mm screws. It's important to adjust the tension of the wires so that the wires, as they run from the front of the frame to the back through the SSD rack, are isolated to the top right SSD slot to ensure there isn't any competition between them and an SSD drive that will be inserted in the second slot down from the top. It really wouldn't matter if there was a little bit of contact between the wires in the drive, but I try my best to minimize that kind of contact. I'm currently waiting on 2 components to finish 3D printing, so we're going to navigate away from the SSD rack and focus on getting the 2 front panels ready in the meantime. I'll tackle the external front panel first. This small panel will have a power button, reset button, power LED, and hard drive LED. This panel will be located near the TV where the machine we're building will be used, and it will connect back to the PC via a 100-foot Ethernet cable. This enables the family to turn the machine on and off without needing access to the locked equipment room in the basement. The panel is constructed using 2 45-degree angled legs and a flat panel with 2 13.5mm holes for the buttons and 2 5.2mm holes for the LEDs. The legs attach to the panel with 2 M2 8mm screws on each side. I'll be using momentary push buttons to turn the machine on and off or to perform a reset. Each button has 2 solderable legs on the back, which we'll use to connect our wire leads, and the main body is threaded to screw on a lock ring and nut to secure them to the panel. For the 2 LEDs, I'll be using 3mm diffuse green and blue LEDs. The green will be used for the power LED, and the blue to indicate hard drive activity. The longer leg on each LED is the anode, or positive leg, and the shorter leg is the cathode, or negative leg, and these need to be hooked up correctly to the positive and negative wires from the computer. LEDs are fascinating little semiconductors. Typically, the color of the LED has a direct impact on the amount of voltage, or more specifically the forward voltage required for it to function, with red requiring the least amount of voltage and white being at the top of the chart with various colors of UV LEDs. The analogy I hold in my mind when working with or calculating LED circuit requirements is as follows. Imagine I've got a bucket, and on one side of the bucket there is a small section of PVC pipe. If I start to pump water into the bucket, I have to pump enough water into it so the level rises, until it reaches the bottom of the PVC pipe before water flows out the side. In terms of an LED, the forward voltage is the amount of voltage required before A, most LEDs will emit their designated brightness of light, and B, a current flow, typically in milliamps, can be measured flowing through the circuit. This is why LEDs are classified as nonlinear diodes, since the voltage and current do not increase proportionally, in regards to how a certain amount of voltage has to be pumped into the LED before the light comes on and before current flow can be observed. I'll start by adding the buttons, so I'll drop the power button into the first 13.5mm hole, thread the nut on the back, and then use a pair of pliers to lock it into place. The reset button will get the same treatment, and with both added, I'll press both buttons a few times to make sure they don't wobble in the slot, and that an audible clicking sound is heard. This is just a quick sanity check to make sure the buttons aren't obviously broken in some way. The LEDs are attached using these tiny black mounting rings. From the bottom, I'll push the LED up and through the ring, which causes the legs of the ring to flare outward, and the interior catches prevent the LED from sliding back out. Next, I'll massage the legs of the mounting ring through the first 5.2mm hole in the panel, and once it's started, press firmly on the front to snap it into place. I'll use the same steps to attach the blue LED in the remaining hole. Here's how things look on the back of the panel once the buttons and LEDs are added. I'm a pretty forgetful person, so I'll use a red Sharpie to put a mark next to each LED, indicating which side is the anode or positive leg of each LED. I've also designed a flat bar that connects between the angled legs for additional stability, and also provides a clasp position for the Ethernet wires I'll be hooking up in just a moment. It sits between the legs like so, and attaches using M2 8mm screws. To get the wiring party started, I'll cut a length of Cat5e Ethernet cable from the spool that measures between 6 and 10 inches. I cut this fragment long, so I've got plenty of working material, but the vast majority of the total length will be cut off by the time it's done. My preference is to first crimp the standard Cat5e plug on one end, so I'll cut away the jacket, cut the ripcord threads, straighten the wires, organize them left to right in the order of light orange, orange, light green, green, light blue, blue, light brown, brown, and crimp the plug onto the wire. After the plug has been added to one end, I'll move up the fragment an inch to a few inches, cut and remove the jacket, snip the ripcord, and straighten the wires. Next, I'll separate the wires into two groups that are pointing toward the button or LED they are aligned to, sit the end of the Ethernet jacket into the clasp, and attach a cover using M2 8mm screws. The overall diameter of the clasp and cover is slightly smaller than the Cat5e cable I'm using, which ensures that when I crank down the cover, the end of the cable is locked into position and has a redonkulous amount of strain relief from the two pieces clasping together. Now I'll start to trim, strip, and wrap each colored Ethernet wire around the button or LED posts according to the pinouts we've used thus far to connect and route the cables on the frame. After they've all been prepared, things look like this. I've also pre-positioned heat shrink tubing on each wire prior to soldering to protect each metal lead once joined together. I use the same materials and techniques demonstrated in previous videos to solder the wires together and have used the heat gun to melt the heat shrink around each lead. I'm not a fan of making unforced errors in my work, and I have to fess up to a silly mistake that forced me to rebuild the wiring for this front panel. I didn't realize I made the mistake until after I had soldered the wires together, but I used the wrong size of heat shrink on the button legs. Since I had to cut the wires anyway, I just started over from scratch. On the soldered legs of the LEDs, 1.5mm heat shrink works just fine. However, the soldered legs of the buttons require at minimum 2mm heat shrink to fit adequately around, and I stupidly put 1.5mm heat shrink over those as well. In terms of construction, I followed the same steps as I've already outlined. I just used the proper size of heat shrink tubing this time around. That completes the construction of the external front panel for the build. Let's now tackle the front panel that will be present on the frame itself. For support of the panel, I cut 3 sections of aluminum, one that measures 75mm long, and 2 that measure 123mm long. They're assembled using interior corner joints and M5 set screws, and I've pre-positioned a silver corner bracket on the inside edge of each leg using roll-in T-nuts and an M5 8mm screw. This assembly will be mounted behind the empty space on the right side of the door, so I'll open the door, put a pencil mark 25mm down from the top, roll in 2 T-nuts, hold the arm in place while lightly threading 2 more M5 8mm screws, slide the arm into position, and tighten the screws down fairly tightly. but still loose enough that I can massage the arm position if need be. What I'm looking to achieve is a uniform distance between the outside edge of the arm and the top, left, and bottom edges of the door metal. Generally, I shoot for a 4mm gap on these sides. Once I've confirmed the gap size is consistent, I'll tighten the screws down completely. Lastly, I'll make sure the door still opens and closes smoothly after adding the arm. On the front of this arm, I'll be mounting this front panel that has the same button and LED holes as the external front panel we made earlier. The panel itself measures 119mm wide, 114mm tall, is 4mm thick, and has pill-shaped mounting holes in each corner that are 5.5mm wide to easily accommodate M5 screws. Behind each corner I'll place these buffer cubes, which measure 20mm wide, 20mm long, and are 18mm tall. With this flat panel being easier to position and attach, I'll pre-assemble and solder the button and LED wire leads and attach them once they've been made. These components will be made successfully the first time using the following materials: momentary push buttons for the power and reset buttons, 2mm heat shrink over each soldered lead on the buttons, 3mm diffused green and blue LEDs, 1.5mm heat shrink over each soldered leg on the LEDs, and 24-gauge stranded wire for all connections. Once all have been built, I'll insert each button and LED into their respective hole in the front panel by tightening the nuts for the buttons with a pair of pliers, and pressing the LEDs and mounting rings firmly into place. With the panel complete, I'll roll in 4 T-nuts into the arm, with 1 in each corner, sit the panel in place with an 18mm spacer between the panel and the support arm, and lightly thread an M5 25mm screw. After 1 has been started, I'll add the remaining 3 spacers and screws in each corner. Before making final adjustments, I'll close and latch the door, and then massage the positioning of the panel until there is a consistent 4mm spacing around the entire perimeter of the panel. Once I get it just where I want it, I'll tighten each of the corner screws down completely. Here's how it looks seated in its final position. On the back of the panel, I'll straighten and trim each wire, strip 2 to 2.5mm of insulation off the end of each wire, crimp a female DuPont connector onto each using the PIBA 2030M micro crimper, and insert the pins into the labeled connector housings using the pin to color wire assignment we've used throughout. Now I'll connect the male and female pins together, insert a T-nut into the vertical bar, attach a cable clasp using an M5 6mm screw, drape the wires over the clasp, and add a few zip ties to keep the wires wrangled in place. Before we can test both panels, I need to whip up a 100-foot custom Ethernet cable, which will be used to connect the external front panel to the machine. The current pin order, when looking at the Ethernet coupler straight on, is brown, light brown, blue, light blue, green, light green, orange, light orange. However, since the Ethernet plugs face the same direction but on opposite sides of the coupler, the pin order will need to be reversed so the same color of wires connect to each other as they pass through. Outside of this important consideration, the cable is a standard Ethernet cable that I've crimped a Cat5e RJ45 plug on each end of. Now that the cable is made and plugged in, we can test both front panels. I've plugged the computer into the wall, and starting with the front panel on the frame, we'll push the power button to turn it on. We can see from the surrounding fans and lights, as well as from the motherboard codes being displayed here, the machine did in fact turn on. The power LED has illuminated and the hard drive activity LED is flashing as the hard drive is being accessed. So the frame's front panel is Gucci. Let's try the external front panel. I've attached another Ethernet coupler to its RJ45 plug and have inserted the other end of the 100-foot cable we just made. Instantly, we see the power LED come on, and the hard drive activity light flash in tandem with the light from the other panel. Pushing the power button on the external panel, we can see that the machine shut down, and when pressed again, the machine comes back online. Lastly, a quick press of the reset button shows that it works as well. Via the monitor I can see in the room that you can't see in the video, and from watching the motherboard code reset as part of the restart. So there we have it, 2 functional front panels with one on the frame itself, and another that will sit in the living room under the TV, and connected via an Ethernet cable back to the machine. There's just something that feels incomplete about a PC build if it doesn't include adding at least one badge someplace. To check that box, I'll put 2 marks at 59.5mm on the front panel with a pencil, and then draw a vertical line connecting them. This represents the center point of the panel. Next, I'll peel off the Gigabyte Oros badge, Place the top and bottom points on the line and press it firmly into place. For now, I'll clean the pencil marks off with the eraser on the pencil, but I'll need to come back later and do a better job with a Q-tip and a spritz of Windex. Let me also briefly explain another reason I really like using Ethernet cable to power the external front panel. In the build, I demonstrated a very simple point-to-point example. However, since Ethernet couplers can be daisy-chained together, if you were to decide that perhaps one of the LEDs was a little too bright, you can easily make up another short cable, snip the positive wire on one of the LEDs, solder an inline resistor into the cable, and then daisy-chain another coupler in place to reduce its light output. I have tons of these kinds of cables made up with different resistors in place, but to show you what I mean, here's a cable with the splice still open to show you how simple it is to craft such a cable. The only thing you need to manage is the order of the wires as they travel through the coupler, to ensure that the colors match up as expected. I've also been known to disassemble an Ethernet coupler's plastic housing and directly solder in resistors to the traces on the bottom of the PCB, but not all couplers have boards that allow for this modification. It is the cleanest and most elegant solution in my opinion, despite requiring a fairly high degree of soldering precision to accomplish. And that's going to do it for this video. We're coming into the home stretch now, so I hope you'll tune in for the next entry in the series where I'll create the power cable for the 20 SSDs, wrap up a couple of very tiny tasks, and finish the build. I hope you've enjoyed this demonstration. Thanks for watching, and out.